Technologies like connectivity, cloud computing, AI, and smart devices to enable inclusive and sustainable development. Since 2019, Huawei has been working with governments, customers, international organizations, scientific research institutes, NGOs, and other partners across different domains. Together, we are using digital technology to help build a more inclusive and sustainable digital world.
These contestants are the seeds, and we believe that they are the key to unlock the sustainable development of the ICT industry.
We're now conducting the 46th and 47th World Finals Championships here at ICPC World Finals Luxor.
It's a great honor for Huawei to be able to support the ICPC World Final here in this beautiful city and long history city. As a leading global provider of ICT infrastructure and smart devices, we value the importance of research and innovation.
For me, the best thing about programming is that whenever you have an idea, you can implement it right away with your own hands and see the result of it. So you can always test something new and create something new by yourself.
They can only find out how well they can do when they compete with others who are vastly talented. Understand, those are top students from the top universities of the world.
Yeah, so the trick is that you probably have to find some smart way to compute things for different AI. It's the first time that I have the opportunity to compete in the World Finals. So what inspires me about competitive programming is that it's very dynamic. You have some hard problems to solve and you can immediately test your intuition and check if your code is correct or not. So I think that this dynamic environment is very exciting. All the people here are very excited about problem solving. They are always interested in learning new ideas. And I think this is a very good environment to be at.
I like the satisfactions of solving hard problems, each problem has some optimal solution, and in the industry we usually have some approximate solution, and we try to optimize it, try to make it better. One particular challenge, that there is only one computer per person, and when one person is stuck on some problem, it's important to help him to try to debug it and together solve this problem and move on in the competition. I want to win the first place.
The traffic is really bad here, but probably with better scheduling, we can have a better traffic in the future. And I was doing the online scheduling, meaning that we're just solving real world problems.
If you look at any of the great utility companies in the world that provide services, they only exist because people trust them. And an example is Huawei is one of the great trusted companies in much of the world and has great technology, but part of the reason that they do is because they have very creative minds who are focused on providing the services that people want. Today's natural resource are human beings, problem solvers, people who can adapt technology to create opportunity for other people.
I don't have any specific answer to how to improve world. I want to do something that would improve the life of all the people in the world.
Hello, I'm Zhang Yifan, a database engineer from Huawei. This challenge is related to database management systems. If you are enthusiastic about programming, I'd like to welcome each and every one of you to accept this challenge. A database is a warehouse where data is organized, stored, and managed by data structure. We are now in the digital era. Productivity systems such as remote office, online conferencing, and distance education are being widely used. Databases play an important role in the bottom layers that carry digital technologies and services. In the digital era, countless devices produce, transmit, store, query, analyze, and process data every second. As one of the effective means of data management, databases have been widely used in various industries and have a far-reaching impact on social development. Databases support a host of services such as online shopping, railway ticket booking, and bank transfer, giving full play to hardware computing power and support application systems. Databases are regarded as the core pillars of IT system. This challenge focuses on shared buffer modules in database management systems. Contestants are required to return the database buffer location of each page access request of each tenant. If a page has been loaded at the location, it is referred to as a hit. Otherwise, it is referred to as a page fault. An increase in the number of page faults causes an increase in disk, thus affecting user experience. Many excellent cache allocation algorithms, such as LRU and LFU, are widely used in cache systems for a single user. However, this challenge involves a multi-tenant environment where contestants need to dynamically allocate the buffer to different users, as well as design appropriate allocation algorithms based on user data characteristics. Contestants can use algorithms to better share and isolate memory resources in a shared buffer pool in a multi-tenant environment, achieving efficient resource utilization and maximizing the overall multi-tenant experience. Contestants can use algorithms to dynamically allocate buffers of different size to tenants and design different allocation algorithms for each tenant based on user service models and data characteristics, reducing the number of page faults in a database buffer. In this change, contestants can use top classical algorithms, combine classical algorithms, or even create excellent algorithms to improve user experience. We hope that through this challenge, programming experts from around the world put forward excellent ideas and solutions. Let's work together to make outstanding contributions to database technologies. Hope you enjoy the challenge. Thank you.
Every year, over 40,000 of us across the world gather for one competition.
Показывают свои знания в программировании и математике.
这个过程苦跟快乐并列着。
Where three becomes one.
3个人其实只能用一台电脑、一个键盘来写代码。
It's one competition where you have to beat your own friends to advance to the world finals.
Where the intelligent meets the ambitious to battle it out.
There is a lot of smart people that they can make you smarter.
Where one company has mentored hundreds of students, turning real-life problems into real solutions.
实际中遇到的一些算法问题，通过数学语言来翻译过来，可以供大家挑战。
The ICPC Challenge was a lot of fun. Combinatorial optimization problems are one of my favorites.
想了解前沿的课题，挑战世界顶级的难题，华为在 ICPC 中的题目是你所需要来尝试的。
Win or lose, we will all emerge stronger, better programmers, bolder dreamers, and game changers for the future.
Я до сих пор не могу поверить в то, что мы выиграли чемпионат.
ICPC made companies come after me, not me coming after them.
ICPC 的比赛其实对我整个人的系统性思维是进行了一个重塑。
它明确了我未来学习以及职业的成长方向。
Hello, I'm Valerio.
Hi, I'm Filippo.
My name is Tommaso.
We are Factan. You work in a team of 3 members, so the strategic part is quite important.
We have different skills and things we like to do, so during the contest we take different jobs.
You have a lot of problems to solve in 5 hours, which may seem a lot, but are actually quite a few if you want to solve all the problems.
The difficulty of the problem is much higher. You maybe have 2 or 3 problems which are obvious, and how to subdivide the tasks between the team members. Working in a team with like other 2 good contestants is really good, since you can have multiple points of view on a problem. For instance, yeah, you have the solution.
Dear contestants, coach, and distinguished guests, welcome to the 2025 ICPC Challenge Championship powered by Huawei I'm Li Mingzhen from Huawei Contest Management Department. This is my co-host.
Hello, good afternoon. And so I guess everybody is as sleepy as me, and hopefully you have enjoyed the lunch, so I am at least not hungry. And there's a coffee break outside. So this afternoon, so we'll have this tech salon session, and I am Jing Bang, and you know me maybe because I am a 2-time world finalist, and maybe I am the president and founder of Universal Cup. And starting from this September, I'm also an assistant professor from the Chinese University of Hong Kong, Shenzhen. So I think I myself is not a good example yet, but an example that from an ICPC participant to a researcher. So I hope that this afternoon session can bring a larger horizon and bring more insight to everybody in this room, no matter you are a participant or coaches. And I think you can learn something or you can have acknowledge something from this session. And we have invited 4 very professional scientists from Huawei, and they are going to give us a very wonderful, interesting topics in several frontier directions. And I will give the time to Li Ming to introduce our first guest, I would say.
Okay, and we have 4 topics from the Huawei experts, and I warmly welcome you to join the discussion sections in this part, and every participant will get a gift. So first, let's welcome the first speakers, Gong Jiong from Asian's Computing Product Department. Let's welcome Gong Jiong.
Hello, everyone. Hi, good afternoon. I'm thrilled to be here to join this salon. So this competition reminds me of like last time I joined a similar competition 20 years ago. So unfortunately, I was the least smart people in that group. So, but now I'm glad to talk to you, such a smart group of people here. And I believe most of you are already pushed the boundary of AI. And I hope my industry experience can help you on your own journeys. So today I'm going to share my story about the AI compilers. So my name is Jiong Gong. I'm a software engineer and architect. So I joined Intel. I started my career at Intel and joined Huawei about 1 year ago. So for the past 10 years, my major focus is one thing. So how to make AI software run fast in a general and a scalable way. So now I'm serving as a senior tech expert in Huawei, working on the high-performance inference architecture. And I also serve as a module maintainer of a PyTorch compiler backend. So in this talk, I will answer the 4 key questions with you. Why do we need AI compiler, first? Second is, how are they designed? Third, what are the key technologies? And what are the best practice? And what has the industry learned? And fourth, what is this field heading? So AI compiler is a very big topic. So I cannot cover all the details today, but I will try to share with you core ideas so that you can build your own the fundamentals you can build on. So first is why AI compilers. So let's start with something you're already familiar with. That is the traditional compiler. So why do we need traditional compilers? it is simple, right? So we don't want to write assembly code by hand. So it's a very painful. It's slow to write. It's error prone. So we want compiler to do the hard work for us. The keyword here is productivity, right? The compiler automates the difficult part. The logic is similar for AI compilers. So AI compiler, the AI researchers, they don't want to, they like Python, right? Because it is simple to write and it is flexible. But they don't want to worry about the complexity, how to optimize their AI programs on a specific AI accelerators like GPU, NPU, etc. So the AI compiler bridges the gap, the similar way as how a traditional compiler does. Right? So the same idea, but different domain. Okay, let me restate that because it is important. An AI compiler takes a high-level AI program, usually written in Python, and convert it to a highly optimized program with maximum efficiency and maximum generality on AI accelerators at scale. So efficiency means it must be fast, right? Generality means it must run fast across multiple models, across a bunch of accelerators. So combine both the efficiency and the generality, we get productivity. So this chart shows a real example about the torch.compile compilation stack, which is the state-of-the-art compilation stack today, and the native compilation stack of PyTorch. So this shows the gains across various models, the real performance gains across various models. The key insight here is that the performance comes automatically. This is very important as new AI models appear almost every week today, right? So we definitely don't want to optimize specific model for specific AI accelerators by hand. It is painful, right? So get performance for free is a huge win. So now let me introduce how the AI compilers are designed. So first, here's a twist. AI compilers, they are also very different from traditional compilers. Let me highlight 3 key differences. First is about the computation. So as we all know, like traditional programming language like C++, they work with single numbers or scalars. And they run step by step. While AI compiler are different, they work with massively parallel tensor data, right? And they run on thousands of compute units in parallel. Second is a hardware architecture. So AI accelerators usually have typically have thousands of compute units and with a very super fast memory unit, right? They are also heterogeneous, meaning they have dedicated units specific for AI math. For example, the matrix multiplication engines, there are also data copy engines and fast interconnect. The third one is the front end. The traditional compiler for C++, for example, they usually know the entire the program structure beforehand, because the program of C++ is usually typically static, right? And they also focus on control flow, while the AI compilers, they're different. They have to work with the dynamic programming language like Python and try to figure out how to convert it to a static graph. And they focus on data flow. So these are key differences that create challenges for us. Let's see how the architecture of AI compilers can solve it. So modern AI compilers, typically they use 3 pipeline stage pipeline. So think of it like a factory assembly line. First is the front end, or graph capture. So the graph capture basically tries to convert a dynamic Python program into a static one, into a static graph. So a typical solution for this is called Torch Dynamo in PyTorch. This is the most successful engine for graph capture. I will touch on the details later. Then the second stage, the middle end. The middle end is basically the compiler's heart. It tries to work on the graph and apply multiple transformations to the graph to make it fast. So typically, it has 2 steps. So step 1 is a high-level graph optimization, which works on the big picture, the graph with tensor operations. And then in the next step, there will be a low-level kernel optimization that focuses on each individual operations. So usually it's lower the graph representation into low-level intermediate representation. We usually call it loop-level IR that focus on not the tensor operations, but a tensor program on the small data chunks of tensor. And these computations happen usually in a loop, so we call it loop-level IR. And then in the stage 3, there's a backend or code generation. So the backend take the loop-level IR and generate the low-level machine code that can run efficiently on AI accelerators. So you might also see there's like a kernel DSL, right, in the middle. For example, Triton language. So this is a mini program that help the developers to efficiently, productively write their single operator, write the implementation for their single operator, or we call it a kernel. Then the main compiler would piece together these kernels. Here I provide an example, a very simple example with ADD and the ReLU implementation that implemented with a PyTorch script or the Triton. Okay, so I have a question to you here. So why is this multi-stage design? So what's the benefit? I have some answers in the appendix. We can touch on them later if time allows. So if the previous architecture felt abstract, let's look into an example. I apologize that for the busy slide, but I'll try to walk you through all the details. This example is based on the torch.compile stack, and you can see the 3 steps clearly in this diagram. So the stage 1, the graph capture. It is Torch Dynamo's job, which will trace through the program. I use the same PyTorch program, ADD and ReLU. It will trace through the program and captures an FX graph, called FX graph is a high-level graph that works on tensor operations. The Dynamo is very clever. So instead of like only focus on analyzing the Python source code, it will try to, it hooks into the Python interpreter and extract the bytecode from it and analyze the bytecode. So as you can see from the bottom left, the box, you can see that there's a bytecode and with the corresponding FX graph. So for example, like the bytecode says, oh, call method, ADD or ReLU. Dynamo will create a node, an FX node call function ADD or ReLU into the fs graph. And for inputs A and B, it will create the placeholder node. And the intermediate tensors will be the edges connection these nodes. Then, in the next stage, it is a graph optimization. So at the high level, we will go through a multiple passes we call graph rewrites. So for example, we will simplify the complex, decompose the complex operations into simpler ones. For example, layer normalization, right? It composes of like variance and mean operations. It will call variance and mean operations instead. It will also annotate the tensors with the shapes and data types. Then the next step, the torch inductor will lower the high-level fx graph into another IR called inductor IR, which is the loop-level IR. So as you can see in this example, inside the inductor IR, we basically fuse these ADD and the ReLU operations inside a loop, in the loop body. This is where the performance comes from. And finally, the last stage is a code generation. So this is the clever part. Inductor would generate it wouldn't generate the native code directly, but it will generate the Triton code for accelerators and the CPP code for CPU based on the inductor IR. So you may wonder, hey, you mentioned that in the last slide, the Triton DSL is the input to the flow, not the output. Why we have output here? Well, think of there's a virtual accelerator which understands Triton and can execute Triton. And this virtual accelerator and then implement it with Triton compiler and CPP compiler and do the rest of the job. So that's the power of abstraction, that we build our solution on top of mature and powerful building blocks. Now let's dive into the key technologies. So let's have a quick recap. So what challenge we are trying to address? First, we need to capture dynamic Python code into static graph. Then we need to make massively parallel tensor computations run efficiently on the hardware with the heterogeneous computation units and at scale. So first is graph capture. Here, the Torch Dynamo is the state-of-the-art solution in PyTorch. It's won over various previous attempts. Why? Because the old solutions like torch.jit, they will force the users to change their code. Make matters worse. They are not sound, meaning that they might fail silently without telling you. So Dynamo fixes all these problems. So Dynamo, as I mentioned, it traces through the program and with a Python interpreter and extract the bytecode, and it will replace the original Python code with the optimized one. It is a compiled code. Then the next time we run into the same function, we run into the optimized code instead. So this gives you efficiency. And the Dynamo also installs guards on the compiled code. So these guards watch the conditions in your Python code. So the next time, if the condition is not met, Dynamo will try to recompile code. This brings soundness. And the Dynamo, if there's unsupported Python language features, Dynamo will just break the graph gracefully and fall back to the original Python implementation. That gives you the reliability. So what lesson can we learn from this? User experience matters most. A compiler that's hard to use or silently break your code, nobody will use it, no matter how fast it is. Now, next is performance optimization. I list a bunch of optimization techniques here, but I will tell you, these techniques are totally not new. They originate from the classical compilers, high-performance computing, and computer graphics. I cannot cover all of them today, but I will give you a big picture so you will know why behind all these techniques. First, we want to reduce the redundant computation as much as possible, just like traditional compilers. Second, we want to minimize the data movement. Moving data is very expensive, much more expensive than the computation itself. So the modern memory architecture, it is hierarchical, meaning the small and fast memory sits close to the computation unit, while the large and slow memory is far away. So the key idea is here is that we try to keep the reusable memory in the small memory close to the computation as much as possible. Also, we try to make the data movement in parallel with computation and access the data in a contiguous way, which is much faster. 3, we want to maximize concurrency because there are so many computation units in the accelerator. The idea is simple. We split the job, right? We slice the data, we split the job, and let them run in parallel on multiple computation units. 4, we try to minimize memory usage so that we can fit large models. 5th, we hope our performance is general so that the optimization can be adapted to multiple models and shapes, etc. Let me show you 2 examples to make this concrete. First, at the high level graph optimization, operator fusion is one of the most important optimizations. So the idea is very simple. We recognize common fusion patterns. Here, it is RMS norm, the fusion, the subgraph, and we replace it with, for example, here, a single operator, pre-optimized, and fused operation here. So the key principle here is that the subgraph before and after the graph rewrite, they should have the same semantics, same input, and same output, and same functionality. So the core technique here is pattern matching. It is like we rewrite the graph based on a predefined rule. The rule is about the operator types and how the operations are connected. So the next is low-level kernel optimization. So this feels more complex, but let's walk through Matmal ReLU kernel in Triton together. So here I will point out the key optimizations. First is the memory access optimization. Let's see section 3. So here we compute the offset into the big matrices that passed to this kernel function. And we try to access the small chunks of the matrices. This is called tiling, right? We try to access the small data chunks at a time so that they can be close to the computation units. so that they can fit into fast SRAM cache. Second one is swizzling. Let's see section 5. So swizzling tried to remap the tiles to different memory banks to avoid bank conflict. Bank conflict happens when parallel threads try to fight for the same memory bank. So swizzling help improve the memory bandwidth. And now let's look at the section 6. It's a fusion. So notice that we compute the ReLU operation immediately after the dot product inside a single loop. So this avoids unnecessary accesses to the main memory. So the second is computation optimization. Let's take a look at the section 2. So basically here, we compute different program IDs for different kernel instances. So the idea is simple. We want to map the kernel instances to different computation units so that they can run in parallel. So this is called parallelization. And then let's see section 4. It is a main loop. So Triton compiler will unroll it automatically. So after unrolling, we can do pipelining. So let's see the diagram in section 4. In each iteration, when the data is accessed and computed in this iteration, we will try to preload the data for the next iteration. So we are doing two things in parallel, right? And finally, let's look at the Triton.AutoTune declaration. This is the auto-tuning technique, which will search for a couple of configurations, like different block sizes, and identify which one is better for your specific shape and the specific accelerator. So this brings generality, making our kernel run efficient on various shapes and accelerator. Okay, so we quickly went through the AI compiler basics. How would the future look like? So I see three major trends. First is the holistic graph optimization, or we call it mega kernel approach. So today, we fuse a few operations. And tomorrow, we will fuse the entire LLM inference step. So the purpose is to avoid the overhead of starting and stopping operations to make our device 100% busy. So the key idea is that we also slice the data tiles and construct a producer and consumer graph. So as soon as the producer completes a tile, the consumer would start immediately without waiting. Second is shifting the performance versus productivity curve. So for decades, we have a trade-off: high productivity or high performance. We cannot get both. We had to choose. In the future, we want to push this boundary using AI to automatically generate the low-level, ultra-fast kernel for us from the high-level Python code. I'm using Helium as an example here. Helium is a new DSL created by Meta that can greatly reduce the kernel development cost. Like an attention kernel only requires 30 lines, while in Helium, while it will require like 120 lines of Triton code. or 1,000 lines in native code. Today, Helium uses auto-tuning to generate Trident code. And tomorrow, the AI-driven code generation will help here. So, number 3, the automatic optimization at scale. AI models are so large today, they have to run distributed across multiple chips. It is hard to optimize by hand, so in the future, we will need intelligent compilers to automatically slice the model, distributed work, and schedule the computation and communication across the cluster. Okay, these are the highlights I want to share today. Again, so it is hard to cover all these AI compiler topics in such a small talk. If you are interested, you can search the internet. There are abundance of materials there. Thank you. Thank you.
Thank you, Mr. Zhou. Is there anybody want to ask a question? Oh, there. Oh.
So the torch compile function can compile any user Python code, but what happens if you give it a NumPy, SciPy, or any other already compiled code? Can it also compile those, or does it revert back to the eager mode for those?
Oh, okay, yeah, that's a good question. So it is always a challenge to support the third-party libraries and convert them into the static graph. So previously, we have to fall back. We break the graph and run the SciPy, the NumPy operations as is. But the new features in PyTorch build a solution that maps the NumPy operation into the torch counterparts, so that we can, instead of running the NumPy, we convert all the operations and the data into the PyTorch counterpart, so that we can trace the NumPy program as is. And then it creates a semantically equivalent program, so that we can construct the static graph with.
Is there any other question?
So I guess the idea here is to try and get as much out of the hardware as you can. Do you have any idea of how much of the hardware is left to optimize? Is there some notion we use 50% of it now, but we could double how fast it gets, or is there some upper bound on the future productivity?
The question is there any upper bound, right?
Yeah.
Firstly, ideally, so the compiler can do as powerful work, as efficient, can deliver efficient program as a human can provide. So the question, I guess, is not the upper bound. The question is how we achieve the maximum performance automatically, right? So actually, this related to the previous questions, why there's a multi-stage pipeline here. So I will just have a quick go through of this slide so that you can have more insight into it. So why we need multi-stage lowering? So the answer is that it provides the abstraction and the composition. So here, the key word is that we can reuse existing building blocks first. Then we can also use what human expert provides. That is a hybrid approach, which combine the automation with the solution from human experts. So at the extreme, according to your question, so like what human can provide is the like upper bound, right? So we do our hard work, write the efficient kernels, and we combine these together. This is the upper bound. And we try to achieve that automatically. We can start with something that human already provides, and then we replace the building blocks with automation. And finally, we reach a state that it is North-Star compiler. Do everything automatically. But in the real industry, the lesson learned is that it's usually more practical to combine these two, like a hybrid approach. So like we can combine some small building blocks with what human provide, like the kernel template. It is not automatically generated. It is just a kernel template provided by human being, right? And we combine these together. So this is more practical. But our dream, so the dream for developers or for AI compilers, the North Star, is fully automation.
Any other question? From behind.
Thank you. Treating seems much easier to write than CUDA, and in some cases, its compilers optimize certain kernels better than the native CUDA. Do you think Triton could eventually replace CUDA?
Yeah, it's a good question. So I guess the answer would relate it to the limitation of Triton. Because Triton tried to make it more general. Like originally it tried to like provide a common DSL that can work across multiple hardwares, right? So we write a kernel once and it can run everywhere. The reality is that the portability only applies to the functionality, not the performance or the efficiency. And still, it is like the trade-off between productivity and the performance, right? It is a trade-off.
Okay, thank you.
So my view over it is that we can really push the boundary. So like Helium, as I mentioned, is one attempt that tries to like automatically generate Triton code. So the code would be not necessarily Triton. It can be like with Triton with extension. So the extension can run more efficiently on specific AI accelerator. So Helium would abstract things out and automatically generate like the accelerator native Triton code. So that way, we can make Triton like probably in the future replacing CUDA, the native approach.
Okay, any other question? So I have a question. So the title of your presentation is about your journey over the last 10 years. So, but you basically described like your understanding of the AI compiler, the past, the present, and the future. So most of us as participants, undergrad or grad students, so one of the questions that we find it very interesting to ask you is that why would you start to study or work on the AI compiler? Like, what's your story? How did you begin the journey? And what's your current thought on your current work?
Yeah. Thanks for the question. So what makes me feel passionate is like automation. So like if there's some day, I don't have to like work like so many hours today. I can have some automated probably AI robots or agent to help me, and I just enjoy my life. That would be great. So AI compilers fall into these categories that can do things automatically for me, right? So before that automation comes true, I have to put effort to it, so that make things automated. You know, we just write simple Python code, and AI compiler will do the rest for me. Yeah, that complies with my dream.
Okay, is there any other question?
And thank you so much for your presentation. It's very nice. So during my days, when I was doing computer graphics, one of the things we encounter when trying to use GPU acceleration is that there is a very large overhead or performance penalty when we are trying to transfer data from CPU memory to the GPU high bandwidth memory. There are a lot of cycles to go through, and when this thing happens a lot, the performance degeneration is very significant. So with PyTorch, are there current or future functions that will be able to minimize such overhead, let's say rearranging the control flow or doing code, especially when we are forced to run in the eager mode?
Okay, got it. So the question was that, so like in the computer graphics, actually it is not only computer graphics. The data movement from the CPU host memory to the device memory is kind of slow, and the bottlenecks the workload, right? Yeah, so this is basically a question about the data movement, how we can optimize the data movement. Well, the first of all, we need fast hardware, right? So like you know, what Huawei provides is the same speed, high bandwidth speed interconnect between the host, the CPU, and the devices. So both between devices and between the host, CPU, and the devices, the same high bandwidth interconnect. So this is first of all most important thing. And secondly, we do have the solutions, the software solutions, as I mentioned, like how to make the data movement faster, right? So like we can do pipelining, like prefetching, right? So we can load the memory beforehand. So this already there in the PyTorch, where there's a data loader in PyTorch, right? So data loader basically try to load the large chunks of data from host memory to the device memory before the model can compute on it. And this loading is asynchronous. So when the computation happens in this iteration, we will preload data for the next iteration. So the similar idea as what I showed you in the Triton example, right? So we do pipeline the preload. And of course, we also need to pay attention to the data layouts in the host memory, so whether it is like contiguous or not, right? So usually it access memory data contiguously would improve performance. Yeah, that's the basic idea.
Thank you. Since our time is limited, so the question session is over. So thank you again for your wonderful presentation.
Thank you all.
Okay. And the next speaker is from Huawei's Semiconductor Department. Let's welcome He Wenbo.
Hi everyone, thanks for coming to today's presentation. I'm glad to share our considerations and some challenges in building AI graph compilers, especially for the computational partitioning problem and instruction scheduling problem. First, let me briefly introduce myself. I'm Wenbo He, and I just graduated from Washington University in St. Louis, where I get my PhD degree in electronic engineering. After that, I come to Huawei Semiconductor Business Department. Now I mainly focus on AI graph compiler and graph partitioning problem. So first, let's start from a trend. Nowadays, the AI models have become larger and wider. In the past, the model usually have millions of parameters, but now they can be billions, tens of billions, hundreds of billions, or even more. And in the past, we have a chatbot, but now we have a reasoner and even agent. Also, In the past, the AI models exist on supercomputers, but now they exist even on some edge devices, such as our mobile phones and network video recorders. So their computational hunger are endless. To feed their computational hunger, Huawei has published several devices, such as Atlas 900 for central training, Atlas 800 for central inferences, Atlas 500 and 200 for edge inferences. For example, Atlas 900 can provide 25.6 pflops at IP16. It's very high, but it's not enough. The raw flops is not the bottleneck. The true bottleneck is how to translate AI programs into efficient silicon execution. That's why we need the AI compilers. Because AI compilers can help us to mitigate these three main challenges. The first one is, how can we fully utilize the onboard memories? If you have ever tried to deploy large language model on your personal PC, you may notice that the memory is a true bottleneck, right? You can afford some slow inferences, but if your memory is not enough, you cannot run the model at all. To do that, we need to consider the memory complexity. Now it's explosioning. We have a deeper hierarchy, non-uniform access, and non-shared memory, and so on. Also, to decrease the bit memory, we need to have the memory reuse. However, it will further decrease the layout flexibility. Also, for language model, we have dynamic batch size and spatial length, which will further decrease the inefficiency in memory layout. Also, to increase the performance, we need to fully unleash the theoretical computing power, that is to say, to reach the raw flops. To do that, we need to have the uninterrupted data supply, which is to avoid the memory wall. Also, we need to balance the test linearity and parallelism, and suitable operator fusion and tailoring strategies. The largest thing is that CUDA C for NVIDIA GPU and Ascend C for Ascend NPU are powerful and flexible enough, so we can actually achieve these two goals. But the problem is, how much human effort needs to be invested to achieve these two goals, right? If you spend 1 month to optimize your model on one agriculture, and then another agriculture comes in and you need to optimize for another 1 month, that's not acceptable at all. Further, modern kernels are highly architecture aware, and kernel development must consider both algorithm and hardware. This figure is a demonstration of flash attention. It's very efficient because the developer of it considers both the software and the hardware, especially the memory layout. So nowadays, only experts in both software and hardware can develop algorithms, the kernels that are efficient enough. That's even more expensive, as we know. The lucky thing is that we have AI compilers, which can make the things a lot easier. That is to say, to mitigate these three biggest challenges. Here is the first compiler I need to introduce, which is Highlight Long. Highlight Long is mainly used on computer vision, not on large language model, on machine learning. But it's very important because it introduces a very critical idea. That is to say, to separate the algorithm and the schedule. Here is an example of a 2D blurry algorithm. The algorithm is writing only in 2-line of code. Blurry x equal to the mean of input, and blurry y equal to the mean of blurry x. It describes our algorithm, but it did not say how we execute it on the hardware. And then there are 3 lines of code to describe the schedule. We first do the tile, then vectorize, then parallel, and compute at some place, and store at some place. And then the highlight line will translate this DSL into a C++ code, and then this C++ code will run on our true backend. So if we want to change our algorithm, we only need to change it to blurry x and y code. And if we want to turn it performance to make it work better on some specific devices, we only need to change these schedule primitives. So this idea of separate algorithm and schedule made our life a lot easier. Another compiler I need to introduce is TVM. TVM is a somehow in-fact standard of a graph compiler, right? It provides a very practical and useful workflow. First, the user will construct or import a model, and the model will come into TVM, and TVM will use many passes to do different kind of optimization, such as graph optimization, common code eliminate, dead code eliminate, and so on. And also we will have tensor program optimization, elaborate dispatch. After that, the optimized code will run on universal runtime. Nowadays, new silicons don't need to write their own compiler. They can use TVM as their front end. So user only need to write some TVM code and run their model on new silicons. So they are very efficient and very easy to use. Another programmer I introduced is Salon. Salon is based on TVM, that is to say, they use TVM as their backend, and Salon use tile as their base unit. So we do program not on double, on float, but on a tile of float, a tile of double, a tile of int, or something. Also, it provides users some flexibility to do optimization. For beginner, they only use tile library to do the hardware-independent programming, such as the right-hand side. The code can be very straightforward, like our just highlighted long code. And for developer, they can use tile library to do the hardware-aware programming to improve their performance, like what we said, the flash attention. And for expert, they can further bypass the tile library and other stuff to directly write the program using thread primitives to further increase the performance. So Salon is now somehow very useful tools, and many new kernels are writing using the Salon. The SandMPU also need to have the graph compilers because of the complexity of the core structure. This is a demonstration of the Ascend 910B DaVinci core structure. As you can see, it has one cube core and two vector core, so it's heterogeneous. And also, it has many pipelines. MTE 1, 2, 3 for different memory transfer, and a cube vector scalar unit for different kind of calculation. Also, the synchronization event number has a limit. There is many memory layout, such as global memory, unified buffer, L1, L0A, L0B, L0C, and other buffer. They are buffer, not cache, so you need to somehow control it by yourself. And also, there are some data paths, so you cannot directly transform data everywhere. And also, the instruction is issuing from a stellar unit, so you cannot assign so many tasks to stellar unit, or the instruction issuing process will be blocked. That is true for NVIDIA GPU, right? Because if you want to achieve peak performance, you need to use PTX, which is, I think, not easier than Ascend NPU. So, as I said before, Ascend C is powerful and flexible enough. In use Ascend C, you can reach peak performance, but the problem is how much human effort is needed to achieve this. With graph compiler, it is expected to achieve very high performance at the out-of-box phase. With some optimization, such as changing some parameters, it can even increase the performance. And in the commercial development phase, we can change other code with some deeper modifying. The performance should further increase at the same level of Ascend C. During the development of a graph partition, during the development of a graph compiler, we found several challenges. The first one is a graph partitioning problem. The user will use AI algorithms and AI models as an input. They will be transformed into a huge computational graph, which is a DAG. I think you know that DAG. And then this computational graph cannot directly run on single code, right? Because if we do so, there is no parallel at all. The performance will be very bad. So our first test is to separate the computational graph into many subgraphs. And then each subgraph can run on different cores. By this way, we have a parallelism. For example, this is a part of the computational graph. where the square unit means the tensor or the tail, and the round node means the operator, the calculation. We separate it into 5 subgraphs, in other words, 5 tasks. The task 1 to task 4 can be executed simultaneously on different cores. After they have been finished, the task 5 can use their output as an input. And when the task 5 have finished, the whole computation graph is finished. During this process, we have some considerations and trade-off. The first one is that we need to balance task granularity and parallelism. If you have ever written the parallel program in C++ or Java, you may be familiar with these two conceptions, right? If the subgraphs are too small, then we may spend a lot of time to do the scheduling and the sorting, so the performance will be low. Also, if the subgraph is very big, then we may not assign same workload to every core, then the parallelism will be hard. The second thing is that we need to minimize the memory copy. Each subgraph will run on a different cores. So at the boundary of the subgraph, the tensor will be copied out to the global memory and copied in to another core's local memory. So if there are many subgraphs, and then there are many boundaries and many data copy, and the performance will be very poor. Another thing is that we need to meet the limitation of memory capacity and the computational operation quantity. That is to say, if your subgraph is very big, then it may have too many tensors. You cannot put them on a single core, and the subgraph cannot be executed. And sometimes the number of operators in one subgraph is also limited, which depend on your compiler. Next thing is that we need to fully utilize the data and the compute pipelines. It's just like CPU. Although you only have one core, but there still exists parallel on that core. For example, we have a copy pipeline and a calculation pipeline. We can do the calculation and copy at the same time if they don't have some dependencies. And also, we need to maximize subgraph isomorphism. Isomorphism means that two graphs are isomorphism if they have the same structure, but different input and output. Here, test 1, 2, 3, 4 are isomorphism because they have the same structure, same operator, but different input-output. They only need to be compiled once and solved once. By maximizing the isomorphism, we can decrease the rate of instruction cache miss and the time of compile and the space to store the program. We can write this graph partition problem into a more formal way. Given a neural network represented by a directed acetylgraph graph, DAG, each node in the graph corresponds to a computational operator. Each operator has two attributes, a resource, which is a memory it used, and the time, which is a time it used. And the resource of the chip has an upper limit, which means that the sum of the resource value of all operators being executed at the same time must not exceed this limit. In addition, there are dependencies among the operators. An operator can only start execution after all its predecessors have completed execution, and our target is to minimize the overall execute time, which is also called match span. I think you guys are expert of algorithm, so maybe you have already come up with some idea to solve it, because it just looked at some little question. It's much simplified. To make it more realistic, we need to add some constraints. The first one is that it should be low complexity. The question itself is NP hard, but our computer cannot accept the NP hard set time complexity. So the time complexity should be ON or ON log n, something like that. And also, the number of cores is limited. Each core has its max resource, which made it more real. Next constraint is that the memory fragment needs to be considered. Well, it's not like CPU, you can just allot and free at any time. The on-chip memory is quite small, so you cannot ignore the fragmentation problem. Another constraint is that the cores are heterogeneous. Operators can only be executed on specified type of cores, which is just like what we have seen before. Da Vinci core have one cube core and two vector core. So some type of operator can only be executed on a specific type of course. Another constraint is that data copy costs are different across chips, right? Data copy in one chip and data copy across different devices and data copy through the network. The costs are absolutely different, and it should be considered. Constraint 6, we need to maximum isomorphism, as I said before, to decrease the rate of edge hash miss. Constraint 7, different type of data movement and computing has its own pipeline. That is less like CPU out-of-order execution. There are also maybe exist other constraints, but by considering those constraints, I think this algorithm are already practical and can be used. There are already some algorithms to do that, such as list scheduling and cluster scheduling. The most famous list scheduling algorithm is HEFT. The idea of it is just assign some priority to each node and sort the node by this priority. However, this list scheduling and cluster scheduling algorithm are usually have quite high time complexity, so they maybe cannot be used on real graph compilers. On some other graph compilers, just like 2AM, there are other set of algorithms to be used, such as thread-based partitioning, min-cut partitioning, min-cut match flow, I think you know that, and also community detection, cost model-based partitioning. However, those algorithms are designed for general compilers. What if we know more hardware details? For example, on the right-hand side, this is a structure of a Da Vinci core. We have the buffer structure. We have the data path. So if we have this information, can we do better? And what if our hardware design can be driven by compilers' design? Can we do better? I think this is a very interesting question. Another question we confront is instruction scheduling problem. In the graph partitioning problem, we cut the original computational graph into several subgraphs. And in these instruction scheduling problems, we need to sort the node in subgraphs to a single chain, because a single core can only accept a series of commands, not a graph, right? So DAG will be executed sequentially. Any execution order that confirms to the topological order is valid. For example, this is a demonstration of the subgraph. There are many sequences that confirms to the topological order. And the different execution order and the memory location planning will lead to different peak memory usage. And the different execution order will lead to different pipeline usage. Here is an example of minimizing the peak memory usage. DAG will be executed sequentially, as I said before, and the memory of a node can be released only after all its successor nodes have been executed. So here we have a small subgraph. We have 5 nodes, A, B, C, D, E. And in the execution order 1, we execute it like A, B, C, D, E. So only after B and C be executed, then the space of A can be released. So by the order of execution order 1, the peak memory usage will be A plus B plus C. Actually, it depends on the memory location planning. We will talk about it later. And in the execution order 2, which is actually DFS, the peak memory usage will be A plus D plus B. So the execution order 2 will look better. Actually, different execution order and the memory location planning will lead to different peak memory usage, right? And we want to have the lowest peak memory usage. The problem of it, to reach minimize the peak memory usage, is also somehow NP-hard, and we can use many greedy algorithms or heritage search algorithms to get the result in a reasonable time, such as BFS, DFS, reverse DFS with some greedy algorithm, heritage search algorithm. Here, the DFS algorithm looks better, but it doesn't mean it is better in any cases. The true subgraph can be very complex. It's not like a tree. So it still depends. Here is an example of the memory reuse method or the memory planning method used in Huawei graph engine. We have a ABCDE, this 5 nodes, and each node has this memory usage. And if we do not do any memory use at all, then the memory cost will be very, very high. And in the step 1, we first run the memory size to the fixed block range. That is to say to 500, 1,000, 2,000, 4,000. And then we use memory with the same size. Here, A and C has the same size. So they combine together, and we call it block AC. And in step 2, we sort blocks based on the size, from big to small. So from E to the green one. And then we do the memory use. That is to say, put the whole block from right to left. And then we have the reuse result. So as you can see, based on this simple, you can call it greedy or heuristic search algorithm, the peak memory usage will decrease by about 50%. So it's very impressive. But the problem is that, can we do better? Obviously, this algorithm cannot reach optimal at every cases, but the optimal still exists here. I have tried before to use a Microsoft theorem prover to try to find a way to get the optimal result. Actually, it gives us optimal result every time, but the computational time is very, very high. It's not acceptable. So can we do it better with some low complexity method? I think it's another challenge. Another problem in instruction scheduling problem is to maximize the pipeline usage. So parallel mechanism exists on a single core by using multiple pipelines. Well, on division core, we have a cube pipeline, vector pipeline, different data transfer pipelines. And different execution order and the synchronization primitives will lead to different pipeline usage. Here is an example. We have a ABCDEFG and this small subgraph, just like a tree. ACE is for copy in. BDF is for vector calculation, and G is for copy out. Again, we have a two-way to do the calculation. The first one is BFS. We first do ACE copy in, and then do BDF vector calculation, and then do G copy out. Then as you can see, AC, this copy, will block the vector calculation, although actually they can. So overall, the pipeline usage is about 60%. It's not high. But if we use DFS, as you can see in execution order 2, we do copy and vector calculation, copy, calculation, copy, calculation, and then copy out. Then the buffer will be almost fully used. So the pipeline usage is about 70%. The more pipeline usage means more performance. That's what we want. To get a better result, we can use BFS, DFS, reverse DSS, and other gradient algorithm, heuristic search algorithm, and so on. So in this instruction scheduling problem, we may come from some challenges. The first one is computational complexity, right? No matter you want to minimize the peak memory usage or maximize the pipeline usage, they are all somehow NP hard. But now you need to have a somehow approximate algorithm to get the good enough result in a reasonable time. So you need to compare the heuristic method and the optimal solution. Second thing is that you need to balance. You need to minimize the memory usage and maximize the pipeline usage. These two goals may not point to the same direction, right? For example, if you want your device can be simultaneously used by different people, as many people as possible, then what you want to do is to minimize the memory usage. But if you are the only user of the device, you want to be as fast as possible, then you want to maximize the pipeline usage. But if there are some middle stage, right, you want to combine these two targets, then it's also a problem. The third thing is that we need to have some flexibility. If we have already designed the algorithm for the given structure, then what if the structure has changed? For example, what if we have more pipelines? What if we have more data passes? What if we have more cores? All right? They are all should be considered. For example, if you use a cost model-based method, then maybe you only need to change your cost model and then everything will work smoothly. But if you are doing it using other such as min cut and other stuff, you directly write the structure hard code in your algorithm, then this kind of stuff will be quite hard. The final thing is that we need to have the worst case success guarantee. That is to say, if there exists the possible solution, you somehow should find it. Although the performance of it is quite bad, then you still should give a feasible solution. It's quite complex and hard, but it's worth thinking. So in this presentation, we have talked about several open problems. The first one is a graph partitioning problem, the instruction scheduling problem. So let's recap it again. The partitioning problem is to cut computation graph into several subgraphs, and these subgraphs will be executed on different cores. Our goal is to achieve parallelism and minimize the topic cost. And the second challenge is instruction scheduling problem, which is to sort the nodes in one subgraph so that they can fully utilize the pipeline and minimize the peak memory usage. If our settings are good enough, then we can have a good streamline, just like the right-hand side. The bubble part will be small, and the overall mid-span, the runtime, should be also small. So our overall target is to have a balance between performance and robustness. We have some key factors. The first is computational complexity. The second is flexibility. The third one is human in the loop, right? If maybe you can let a human be a part of the algorithm. You can give a human some authority to change some parameters to get a better result. It's also another topic. So we'll come to challenge these critical problems in AI compiler designs. As you guys are expert in algorithms, so maybe you guys shed some light on these hard challenges and made everything work. So yeah, thanks.
Okay, any question?
Okay, you said that graph partitioning is what divides the operations to tasks that are executed on the cores. So you also said that there is upper and lower bound on how it should be partitioned, so the performance is somewhere in the middle. Because too little partitioning and too much partitioning is bad for different reasons. Okay, is there a determined algorithm of partitioning, or there are some different algorithms that are used for now?
Yes, there are. I think you asked. There are some algorithms to do the partitioning, right? Yes, there are several methods to do the partitioning. For example, the min cut partitioning, right? We use min cut. Min cut matrix flow. I think you know that. We first cut graph to two parts, and we again to cut it until it's small enough to be executed. And on each cut, we make the two parts have the less community between each other. So community means copy data. So in this way, we can minimize the cost of data copy. Yes, and by constraining the size of each subgraph, we can make the subgraph not very small. Yeah, this is one way to do that. Another thing is that we can use a cost model-based partitioning, right? We can first assume that every subgraph has one node, and then we try to connect each subgraph. We use cost model to evaluate whether it will make performance better or worse. And in the end, we do many times of merge. In the end, we have our subgraphs. So one way is to chart, one way is to merge.
Okay, so does dependencies between tasks affect the partitioning algorithm?
Yes, they are partitioning. Yeah.
It's not what I mean. I mean that dependencies between tasks are making the tasks different, so they will be compiled differently. I mean, if we have two similar tasks but different dependencies, does they still be the same for the partition graph?
Well, I think it depends on what algorithm you use, right? If you use the min chart partitioning, then you assign, you consider the weight of the page as a memory, the memory transfer, the memory size. So if it's large enough, if it's small enough, then the min chart partitioning will chart it. So it depends on the sequence of your chart. So if two graphs are similar, but they have been cut in the different rounds, then they may be different. So the isomorphism may be broken. I don't know whether it's what you asked. Yeah.
Okay, thank you.
As I know, maybe most of the times, the nodes in the ground is very, very large. The number of the nodes is very large, so it's very difficult to partition all the graphics. Maybe we need to make a very simple algorithms to participants into some subgraphs, and then we analyze the subgraphs. For example, you need to minimize the memory dependency. You need to find the minimal cuts in the subgraphs, and then we can separate again and again, like this maybe. Okay, any other questions?
Hi. So during your presentation, you talk about a lot of well-defined problems. So my first question is that how well these questions are exposed to the academic world? Like, can you find the paper in industrial?
Well, I think here, list scheduling and cluster scheduling are totally autonomic. You can find a lot of paper on maybe ACM about this list scheduling and the cluster scheduling. But for the real use, the AI graph compilers, their algorithm maybe not that new. For example, they may use a cost model-based partitioning. It depends on your cost model. So as I know, it's both academic and industrial, right?
Yeah, so how well the academic method work on the real industrial? Like how many % of your work are based on the academic paper?
Well, actually, I'm not sure about it. Yeah, maybe I need to try it later. Yeah.
Oh, okay. So another question is that I know that you are a PhD student until last year. So how well are these problems aligned with your PhD thesis?
Well, in my PhD, I mainly do research about optimization. In that time, I can use some solver to get the result. Even though the solver's complexity is high, but usually we ignore it, right?
Oh, so just like a prover?
Yeah, yes, a prover, yes. But in this case, we cannot use a prover because of the complexity. So it's not an easy transfer, but the idea of it is the same. We don't use the solver, but we use a solver's algorithm to try to do the optimize directly. So yes.
Mm-hmm. Okay. Yeah. And another question is that why do you join Huawei after you graduate last year?
It's an interesting question. There are many reasons. Because Huawei is the first company that gave me the offer. This is a very important idea. And also, I think Huawei is a very great company. It has a very great future, I think. Maybe you know that the hardware of Huawei has been used around China. And only by this way, our algorithm can be used not only on academic, right? We can apply our algorithms, our work on real platform. That's what we want. Yeah.
Okay, thank you.
Okay, because the limitation of the time, we had a last question. Oh, sorry.
Yes, so in this task scheduling problem, I mean, it must depend a lot on how much time a task takes. But do you know beforehand, or how do you know beforehand how much each time a task will take?
Could you say that again?
I mean, so in practice, you have to somehow estimate how much time each task will take.
How much time you need to pay, right?
Or how do you know how much time it will take?
How much time it will take? Well, actually, we don't directly care about the time, especially we care about the time complexity. So if it's O(n) or O(n) log n, so we think it's usually enough, right? It's a compiler, not a controller on the drone. So even it's a little long, but it's not too long, it's acceptable. Right? We care about the time complexity.
But I think, okay, can you go to the slide with the scheduling problem?
Yeah.
With the so change slide to the where you compare the different
and the A be released, and also it's using order 2. When B and C be executed, and A will be released. Yes.
Yeah, so my question is, how do you? I mean, to solve the problem, you need to...
Okay, I can explain. And you mean the timeline? It means the timeline from the beginning to the end. And that means the task executed order is A, B. B and C is parallel in the lab's graph. B and C is parallel. B and D is also parallel. And from the timeline goes through from the top to the bottom. Is the timeline. That means the task, when the task will execute, okay, and the memory line is the memory's usage. So as the expert says, when the B and C has ended, before the ending of the B and C, the memory captures by the task A cannot be released because the output of the task A is the input of the task B and C. So you can see the empty cells in these pictures. That means the task A has ends, but the memory of the task A cannot be released. So it captured an empty memory usage like this. So you can see the timeline from the top to bottom, so execute and memory usage. Can you understand what?
Yes, thank you.
Okay. Okay, so thank again to He-Wen, and then we had 20 minutes coffee breaks. Then you can go outside to breaks and enjoy the coffee and tea, and you can communicate with each other. And we will come back after 20 minutes, okay? Thank you.
2.7 billion people around the world still have no internet access and don't know how to use the internet. How can we bridge this digital divide? In the face of climate change and biodiversity loss, what can we do? While the world presents innumerable challenges, technology continues to offer innovative solutions. Let's use digital technology to protect remote mountain areas, oceans, forests, wetlands, and other areas. Let's help senior citizens, women, children, people with disabilities, unemployed young people, and everyone else access the digital world. Let's work to empower everyone with digital capabilities and better protect this planet that we call home. Through multilateral cooperation, we can leverage digital technologies like connectivity, cloud computing, AI, and smart devices to enable inclusive and sustainable development. Since 2019, Huawei has been working with governments, customers, international organizations, scientific research institutes, NGOs, and other partners across different domains. Together, we are using digital technology to help build a more inclusive and sustainable digital world.
These contestants are the seeds, and we believe that they are the key to unlock the sustainable development of the ICT industry.
We're now conducting the 46th and 47th World Finals Championships here at ICPC World Finals Luxor.
It's a great honor for Huawei to be able to support the ICPC World Final here in this beautiful city and long history city. As a leading global provider of ICT infrastructure and smart devices, we value the importance of research and innovation.
For me, the best thing about programming is that whenever you have an idea, you can implement it right away with your own hands and see the result of it. So you can always test something new and create something new by yourself.
They can only find out how well they can do when they compete with others who are vastly talented. Understand, those are top students from the top universities of the world.
Yeah, so the brick is that you probably have to find
some smart way to compute things for different AI.
It's the first time that I have the opportunity to compete in the World Finals. So what inspires me about competitive programming is that it's very dynamic. You have some hard problems to solve and you can immediately test your intuition and check if your code is correct or not. So I think that this dynamic environment is very exciting. All the people here are very excited about problem solving. They are always interested in learning new ideas. And I think this is a very good environment to be at.
I like the satisfactions of solving hard problems. Each problem has some optimal solution, and in the industry we usually have some approximate solution and we try to optimize it, try to make it better. One particular challenge that there is only one computer per person, and when one person is stuck on some problem, it's important to help him to try to debug it and together solve this problem and move on in the competition. I want to win the first place.
The traffic is really bad here, but probably with better scheduling, we can have a better traffic in the future. And I was doing the online scheduling, meaning that we're just solving real-world problems.
If you look at any of the great utility companies in the world that provide services, they only exist because people trust them. And an example is Huawei is one of the great trusted companies in much of the world and has great technology, but part of the reason that they do is because they have very creative minds who are focused on providing the services that people want. Today's natural resource are human beings, problem solvers, people who can adapt technology to create opportunity for other people.
I don't have any specific answer to how to improve world. I want to do something that would improve the life of all the people in the world.
Hello, I'm Zhang Yifan, a database engineer from Huawei. This challenge is related to database management systems. If you are enthusiastic about programming, I'd like to welcome each and every one of you to accept this challenge.
A database is a warehouse where data is organized, stored, and managed by data structure. We are known in the digital era. Productivity systems such as remote office, online conferencing, and distance education are being widely used. Databases play an important role in the bottom layers that carry digital technologies and services. In the digital era, countless devices produce, transmit, store, query, analyze, and process data every second, as one of the effective means of data management. databases have been widely used in various industries and have a far-reaching impact on social development. Databases support a host of services such as online shopping, railway ticket booking, and bank transfer, giving full play to hardware computing power and support application systems. Databases are regarded as a core pillars of IT system. This challenge focuses on shared buffer modules in database management systems. Contestants are required to return the database buffer location of each page access request of each tenant. If a page has been loaded at the location, it is referred to as a hit. Otherwise, it is referred to as a page fault. An increase in the number of page faults causes an increase in disk, thus affecting user experience. Many excellent cache evacuation algorithms, such as LRU and LFU, are widely used in cache systems for a single user. However, this challenge involves a multi-tenant environment where contestants need to dynamically allocate the buffer to different users, as well as design appropriate evacuation algorithms based on user data characteristics. Contestants can use algorithms to better share and isolate memory resources in a shared buffer pool in a multi-tenant environment, achieving efficient resource utilization and maximizing the overall multi-tenant experience. Contestants can use algorithms to dynamically allocate buffers of different size to tenants and design different evacuation algorithms for each tenant based on user service models and data characteristics, reducing the number of page faults in a database buffer. In this change, contestants can use top classical algorithms, combine classical algorithms, or even create excellent algorithms to improve user experience. We hope that through this challenge, programming experts from around the world put forward excellent ideas and solutions. Let's work together to make outstanding contributions to database technologies. Hope you enjoy the challenge. Thank you.
Every year, over 40,000 of us across the world gather for one competition.
Показывают свои знания в программировании и математике.
这个过程就苦跟快乐并列着。
Where three becomes one.
3个人其实只能用一台电脑、一个键盘来写代码。
It's one competition where you have to beat your own friends to advance to the world finals.
Where the intelligent meets the ambitious to battle it out.
There is a lot of smart people that they can make you smarter.
Where one company has mentored hundreds of students, turning real-life problems into real solutions.
实际中遇到的一些算法问题，通过数学语言来翻译过来，可以供大家挑战。
The ICPC Challenge was a lot of fun. Combinatorial optimization problems are one of my favorites.
想了解前沿的课题，挑战世界顶级的难题，华为在 ICPC 中的题目是你所需要来尝试的。
Win or lose, we will all emerge stronger, better programmers, bolder dreamers, and game changers for the future.
Я до сих пор не могу поверить в то, что мы выиграли чемпионат.
ICPC made companies come after me, not me coming after them.
ICPC 的比赛其实对我整个人的系统性思维是进行了一个重塑。
它明确了我未来学习以及职业的成长方向。
Yes.
Hello, I'm Valerio.
Hi, I'm Filippo.
My name is Tommaso.
We are Fact 10. You work in a team of 3 members, so the strategic part is quite important.
We have different skills and things we like to do, so during the contest we take different jobs.
You have a lot of problems to solve in 5 hours, which may seem a lot, but are actually quite a few if you want to solve all the problems.
The difficulty of the problem is much higher. You maybe have 2 or 3 problems which are obvious, and how to subdivide the tasks between the team members. Working in a team with like other 2 good contestants is really good, since you can have multiple points of view on a problem. For instance, you have the solution of a problem almost figured out, but you need like that one little missing piece. You can just ask the other teammates, and it will make it much easier.
I think the most fulfilling moment in ICPC was qualifying to World Finals on our first attempt. The most useful skill is learning to learn. And of course that can be applied to many other fields. The most exciting part, of course, is if you get the problem correct, for example, in the last 5 minutes of the competition.
I'm Antoni Długosz.
I'm Jacek Salata.
My name is Grzegorz Gabriel.
We are Team Jagiellonian Drużyna.
There's a lot of things you learn during the ICPC which have a carry over to basically anything you want to do later in your life. And these abilities are just general problem solving and being able to handle really abstract, large ideas in your head really well. I started in ICPC contest for 5 years. I've qualified 2 times to ICPC World Finals. What I like the most in this contest is that I have an opportunity to do some abstract thinking.
I would say our strategy for difficult, hard problems is collaboration, as I individually might not be able to solve a problem, but when collaborating and asking for help my friends, we can together solve a problem as a team. Another thing I would say is that ICPC contests provide a unique opportunity to meet the brightest minds in the world. Meeting new people, learning from them is just great.
Welcome to the 48th Annual ICPC World Finals here in Astana, Kazakhstan.
我们价值体系是要为人类服务。
From an independent startup to one of the world's top information and telecom technology providers, Huawei connects and serves more than 3 billion people across 170 countries and regions. Working with top minds, We are building a fully connected and intelligent world. Our networking and AI solutions transform lives for the better. In mining, manufacturing, transportation, energy, finance, healthcare, education, retail, internet, public services, and the ways we increasingly interact in and go about our daily lives. Huawei transforms. We invest in fresh ideas and constant innovation. We believe in open collaboration and partnership. We care about our employees. We care about developing talent that can shape the future. We care about the communities we work with and live in. We care about the health of our planet and are dedicated to actively protecting it.
高43动拐次下升线，广州。
部位在哪里？你用手指给我看一下。这个位置。你把手放到仪器上，我们会把对你的数据监测传给刀的尼克。
Elettrocardiogramma che tiene un'arritmia leve.
Okay, everyone, welcome back to the Tech Salons. And I hope all of you had made a friendship with each other, because we hope the Challenge Championship event is not only the contest, but also a platform, a chance to make friends with each other. For example, actually I can see very old friend, very old friend, but also I have met some new friends, especially some of you. We only communicate online, but today is the first time we meet face to face. So we print your CF handle in your badges that you can for the contestants. So for you, I hope you can use this to meet maybe you had some online friends, but you had not see in daily lives. So it's the chance to make new friends with each other. Okay, let's back to the tech salon. The next picture is from Huawei Central Software Institute. Let's welcome to Yu Tao. Welcome.
Hello everyone, very happy to share a very popular topic, which is agentic system in this talk. Okay, so a very brief introduction of myself. So my name is Tao Yu. So I'm currently a tech expert in the Huawei Central Software Institute, where mainly I focus on building agentic system. But before Huawei, my previous 8-year industry experience was in Booking Holding and Alibaba, where I do a lot of traditional NLP like multilingual language understanding, dialogue system. That's okay. So I will try to cover about 3 parts. One is about like very non-technical background of this agentic system, and one self-evolving agent. And some second part is about our practice on self-evolving agent, and the third part is some Huawei's effort about our 9agent platform. Okay, so now people keep saying about this agentic system because, like they say, this year, 2025, is a year of agentic. So I think in GTC 2025, they trying to break down, there are 4 eras in the AI. One is about 10 years ago, we called perception AI. At that time, it's like the beginning of the deep learning. Where people trying to building very uniform methodology to model the, like say, different modality like voice, image, text into uniformed representation using deep learning method. And the second era is called generative AI, where like in 2020, and the first version of the GPT was released, and also we have like stable diffusion. Now the general capability of the model and the AI was discovered by the people, and people find this quite powerful. And since for this year, 2025, now among all the world, now people are trying to using all these very powerful foundation models, trying to building like agents, we can call it agents, we can call it like LM applications to solve very complex tasks and trying to solve some really life problems to make the world better. I think people also trying to project maybe by 2030, we can have like say fully automatic vehicle or embodied AI, robotics, and just can be more amazing. So I think for this year, there are several reasons that drives people from like building foundation models to agentic system. One is because now we already have some very quite powerful foundation models. It used to be like only like say for GPT 3.5, it's only support very fundamental like say dialogue capability, and then now we have the function call capability, and now because of the powerful training and the model parameters, we can try to have say long sequential task solving capabilities, and also we are supporting like more unified multimodality. Say we can try to have say voice, images, text all fit into one models. Another part is like we have a very fast growing ecosystem for like say agentic MCP server. I think at the beginning of this year, when Anthropic first released the MCP protocol, I think there are only like very few available sources for MCP servers. But if you check it now, I think there are some, like say, online market of MCP servers. There are thousands of MCP servers. So that's all support people trying to build very, very powerful agents. Also, like so many investment was falling into this AI field that makes people, but how can we actually getting the investment back for some profit? That means you need to be, you need to get this profit from this in-depth domain-specific customers. That means, so we already see like some successful use cases like Harvey.ai from the law side, and also I think all of you like using coding agent. For me, myself, my mindset got refreshed multiple times for this year. First Cursor, and then Cloud Code, and just before my account got banned by Anthropic. And also like, so if you check on the YC's list, you know, just for this year, a lot of the investment from YC is also about this agentic AI. So I think when maybe like 2022, first the GPT 3.5 was released, I think the definition of agent is just simply trying to follow your prompts, follow your instructions. So you can build in like intention recognition, you can build in some like email auto reply. So all these applications you are trying to build is kind of easy, but now we have more powerful foundation models. We have better ecosystem of tools, and also we have more computing resources. So now the agent is more like, say, trying to from a very solving simple tasks to a very complex tasks. So if you can see like maybe manuals, we can using agents to operating a computer fully automate. We can try to let the agents to control a browser fully automate, and then trying to go for a deep search task and go for like to help you to reading papers, trying to do some very high level calculations. I think in Google there's a paper about it called AlphaEvolve. They are also using they're also trying to building an agentic system, trying to design a very state-of-the-art for algorithms, like say how do you schedule the different servers, how, you know, like also very compilers as well. But even though we have very, very powerful agents since this year, we are still facing a lot of problems. And when we try to deliver our agents to our customers, I think a lot of our customers were complaining about like this, they call debugging, because there's one nature that was like limited the, you know, development of agents, which is like static. So once you have a model, once you design the system, and then it's there. And then when you deliver to your customer, and then your customer will see that it's not working as they expected. Maybe there are some very good showcases, but sometimes when you see a bad case, you don't know how to make it better, how to optimize it. So this kind of lacking evolutional capability. So the second part is like, okay, I want to make it better, so I want to change it, but it's actually the, you know, debugging or optimizing cost is super high. So either you need to someone who can do who are very experienced in prompt engineering, or maybe you find your workflow is not working as expected, so you need to change your workflow, you need to change your topology, or maybe you find you need to, your current tools does not support you to achieve the goals you want to achieve, then you need to maybe coding out some new tools, or maybe even maybe you need like the models is not good enough. It's not domain specific enough. You need to retrain or do some post training of your models. That's all kind of maybe for IT company, yes, but a lot of the customers, they are doing their focus on their own business. So optimizing and debugging is very costly for them. That's why we need this kind of a system, like a optimization framework for agent that can learn from experience, that can learn from good experience, bad experience, and trying to automatically optimize itself. That's very important. So the self-evolving agent technology is like growing from 2024. I think in last year it's mainly from the academic, a lot of universities and scholars trying to have some papers to focus on different perspectives. And from this year, a lot of industry companies also trying to invest heavily, trying to release their own, like say, platform or product that can optimize an agent. So a quick overview of self-evolving agent. So what's to evolve? Usually there are like 4 perspectives that needs to be optimized or evolved during the agent execution. So one is the context. So people keep saying the context engineering or prompt engineering, that all part of it. Like say how you maybe your prompt is not like optimized enough. Maybe the context you are given to you are sharing with the agent is not good enough. How can you optimize it automatically? So the second part is more like models, right? When you try the models doing function call, tool calling, does not understanding the task specifically, does not understand the tools very good. So you need to make sure that your model can handle that also part. So the third part is also we call tools. Like say we define a lot of tools for agent, but sometimes maybe the tool is not good enough. So you need to come up with new tools when there's new query or new task come up. Or sometimes now, because MCP is very popular, but developers does not define MCP carefully. So maybe you're just trying to connect some MCPs, but they do not try to, like say, have a clear definition of their MCP. They say, hey, this is a search engine MCP, but maybe it's just like for very in-domain search. So we need like the agent to understand or maybe explore that there's a boundary of these tools. So the last part is about for a multi-agent system is the structure or architecture of an agentic system. So just for workflow as an example, when you're trying to maybe solve a math problem using agentics, you can using just simple one node. We can just feeding all the prompt instruction in this one node. We can call it like a single agent. Or maybe you can have like say a planner, a solver, and a reviewer, and that's another topology. But what are the best topology? So that's another problem we want to try to figure out. So when to evolve is like maybe the evolving or the optimization can happen during the task was solving. So that means or maybe offline. That means maybe for this ongoing task, it cannot be better, but I can learn from the failure and then can be better in the next when I see a similar task next time. So how to evolve? I think so. Currently, if you are just training the model, you're really still like forced into the reward-based reinforcement learning. And when you are trying to like say finding a better topology about the agentic structure, usually heuristic search is a very popular method recently. And also like there's also like self-evaluation, self-optimization when you're trying to do like context engineering or context optimization. So and also like when we're trying to where to evolve, it can be like in a very general agent. It can be on like coding agent, can be a GUI agent, on a financial agent. It's quite up to your use case. Evaluation is also quite critical in the in this self-evolving agent, because collecting the ground truth for agents is very, very challenging. So usually there are 2 common ways to handle that. One is just you are using large language model as a judge, so you can just using, and another part is trying to using like contrastive learning. So basically, maybe you do not know this is really good or really bad, but you know whether this is relatively good, relatively bad, and using that signal to optimize your system. Okay, so the next part I will briefly talk about some of our practice and exploration on this self-evolving agent. So this is a paper that from CGIAR 2025 that we called Instruct RAG. So the background is like So large language models, usually when we talk about agentic system, we take it like a planning action. So you do the thought, action, observation. A lot of like agentic framework falls into this definition. But RAG can help large language model do planning when you're trying to leveraging external databases. Usually we call this kind of experiences, right? So we want trying to get some good experience or bad experience to help us to do the current work better. But usually there are two challenges. One is enlargeability, and the other part is transferability. So enlargeability is like when you have, say, on this task 1, I failed, and then I see another task, I want trying to avoid a similar failure, but nothing is actually exactly the same. So how can we try to maybe have a more general experience in general instead of directly copying the most similar experience? And the transferability is like, say, I already learned a lot of things in maybe, say, math domain, but how can I try to copy this experience into a financial domain or medical domain? That we call transferability. So we design for this planning task, we try to define it as a directly traversed graph. So for each of we have like 3 stages. One stage is we call like building graph, and the second stage is trying to learning an agent that can help us do the planning, and the third stage is called we want trying to have an agent help us to getting some just relevant experience. So building a graph, the purpose of building a graph is trying to have a definition of the planning. So because if you're just like say taking one full task completion trajectory into the as an experience, then it's very difficult to enlarge it because it's already there. You cannot find identical problems in the future. So we need to break it down into some very high level ideas. So we're trying to break down this. We're trying to break down the task execution into some very high level steps. Maybe say first do searching, then do some reviewing, and then do some like cross reference check. This kind of very high level steps. So for every task, we are trying to break down this kind of high level node. So each node means one instruction or one small problems. And then the second part is like then one execution is just trying to like from this small subtask 1 to subtask 2 is trying to having an edge in the graph. Then that means so one pass in this graph, that means solving one full task. And so the second part is building a agent that can help us do planning for a new coming task. This is more like say this is more trying to getting the best path when given a query. How we trying to get the path can solve the given problem. So that means like so if you can see the middle side, there's no laser here. So it's like you can see the red path for a given problem. Maybe that's the best solution. Maybe it's not seen in the training set, but that may be the best solution path. So you need to able. So given the current visited node and giving the current the new coming queries, we want trying to do some ranking of the existing the neighbor node, which one I should pick next to solving the current problem. So the third part is like I also, besides of like say planning trajectories, I also want to have like some references from like say it's no need to be like able to solve the current problem, but just similar enough so I can just use it as a reference. So I just want trying to select the most similar tasks and most similar trajectories. So in the and then so like during the training, so we are using like our agent trying to do the say planning path searching, and we are using like a meta-learning agent trying to find us some examples for the transferability. So that means like we are using so this is like we can train this model in a joint way. So when the R agent trying to do when the R agent trying to select the path from the for the given query, it helps for the ML agent to try to finding the relevant experience, and then I do the execution. I try to evaluate the execution, and then getting the reward about whether my planning is good, and then it can guiding for a better planning process. And so that means, like, say, in the training stage, we have some scene tasks that help us trying to building this graph, and also like we call it instruction graph, and so it's trying to help us sample the batch of data, optimizing the R agent for planning, the ML agent for transferability, and then for the future learning stage, it's more like trying to say, when I have a new domain, when I have some new tasks, so I need to like updating my planning agent, and also trying to updating my, say, the meta-learning agent for transferability. So we also trying to do some experiment on the Hardware QA, ALFF World web shop on this more like for reasoning, embodied task, web shopping, and sense reasoning. And so like we're trying to do some experiments, and all this kind of shows we have better accuracy on the effectiveness perspective. So the third part is now trying to introduce a brief introduce about Huawei's 9问 agent platform. So in Huawei, we are trying to build an industry-leading agent platform that through it consists about both workflow control, multi-agent collaborations, and agent self-evolution. So basically, it have multiple parts. One is about, like, say, we have very fundamental layer that you can run different models, you can connect to different model providers, and on top of it, we have also like a running layer. You can actually we call it high code level. You can build in your agent with the from a very feasible way, and then on even top of it, you can also try to using like N8N or codes or define this workflow way. Just drag node, trying to build your own workflow, and on top of it, we also trying to build in our, like, say, self-optimizing algorithms into this. You can using it to optimize your prompt, optimize your context, optimizing your tool, or even optimizing your topology. So yes, okay. So this is briefly my talk. Thank you, everyone.
Thank you, Mr. Yu. Any question?
Okay, thank you for the good talk. And but my question is, so you mentioned that the agent can self-evolve, right? And but if we make the agent self-evolve and make it more and more customized to a certain task, and is it possible that the agent will forget how to perform other tasks, which is about like we can also call it like overfitting, right? Is overfitting a kind of problem that introduced by the self-evolve? And do we need to consider this?
Yes, I think yes, it is possibly will happen because it's like an optimizing problem, right? You cannot guarantee you are optimizing for this distribution, and then for another distribution it may not work. But I think that's why we want to introduce this self-evolving methodology, because maybe it works on this domain, on this distribution, but later on you see another distribution is not work, but it can be still keep evolving for that new tasks.
So do you mean overfitting is actually what we want, right? So we want to make the agents that are more customized to a certain field.
Yeah, so I will not say it's overfitting. It's more like have the capability of adaptations. So it can adaptation to this scenario and then adaptation to another scenario.
Okay, thank you.
Hello, I have a quick question. So I think there are two schools of thought here, right? So one is trying to use one agent that has every capability versus using multiple different agents, each of them doing a specific task or a specific domain of tasks. So I'm wondering, from your perspective or in Huawei's side, which side of the camp you're in and why?
Sorry, I didn't hear your question clearly. Can you repeat it?
Sure. So one agent doing everything versus a specific agent doing specific tasks.
You mean like general agent versus special agent?
Yeah.
I think it's quite like, say, usually on a business domain, we need some specific agent, but it's one more like on say a 2C customer-facing product. Usually we need some like more general agent. That's from what when we see the customer, that's our best practice. But for this optimization or self-evolving, it just works for both.
Yeah, thank you for your great talk. So my question is that maybe there's a possibility that the model may evolve in the wrong direction, too far away, such that it may fail. So do you encounter such a situation, and how you maybe do something with this? Yeah, thank you.
Sorry.
So is it possible that the model may evolve in the wrong direction and may go too far away that it cannot go back?
Yes, I won't say it's not. I won't say it's not possible. So that's why, like, I think it's more like, say, others says like, say, are you trying to maybe when you're trying to do this optimization, you just to go too far away and never get back to the right track. I think in the traditional machine learning, that's why we have the penalization, right? And trying to make sure it does not go too crazy for your model. And also like for this self-evolving usually is more like, say, that's why we have some, maybe we call it guardrail and this self-evaluation, trying to like say, like precautious for this to happen.
Thank you for your talk. What about useless agents that model don't use at all? Just they don't change anything, and the model just recalculates them, and that's wasting resources. And do you think about it like finding the most useful agents in your model? What do you think about it?
So you mean like the model? Sorry, I did not fully get your question here.
I'm saying that some agents can become useless, like they don't change the result of total model at all. And
yeah, now I get your question. It's more like, say, if you're saying maybe the agents and the model are coupling very tightly. So that means maybe if the model is not good enough, maybe the agent is not good enough. Something like that?
No, I think we can think about add some agents to model that just that overfit of model. That's hard to explain for me.
But maybe I can just, regardless of this specific question, I can talk about the relationship between agents and models, because this is people keep asking to me, and maybe like, and also in this industry and academy. It's like, do I need to build an agentic system because we have more and more powerful models, like say. But my question is always, yes, we still need to building and like say research on this agentic system, because I think one reason is like models are more kind of generous, but agents are trying to more solving like say specific tasks. So that's point number one. And another point is like say there are something, because when we say, just say, we're trying to say, I keep saying learning from failure, learning from success, but trying to learn these things into like a parametric parameters, I think the efficiency is very slow, and the performance and you cannot guarantee it can be learned fully, and that's why we trying to building some like say beyond the model. We have a system that can maybe trying to have more able to following this experience rather than just learning into models.
Thank you. I'm actually very interested in the graph representation of the when the model needs to answer a query. Mm-hmm. And my question is, let's say the model is retrained, and then the graph where the task and the steps to achieve the task is rebuilt. Will the method of training take into account the size of this auxiliary graph in the model that is built, and how big is the impact? Like, if the retraining is done multiple times, and does the size increase by a lot, and does it impact the performance of the model?
So for this graph building is not part, I want to say it's the training part. We are trying to building the graph from the training data and trying to make sure the graph size grows like linearly with the size of the data. So that's why we're trying to merge the node and merge that's why I keep saying it's not just like the node is a high level instruction. It's not like say search Google for this query, it's more like searching. So that's why we are able to merge the node and then keep the size of the graph in a like say handleable way.
I see. And to merge the nodes, do you use a specific clustering technique to identify which task can be grouped into one?
Yes, that's during the graph building phase. Like when we see a new like subtask, and then we're trying to see whether it's similar to the existing nodes, or it's worthy to building a new node for this subtask.
I see. Thank you.
Since time is limited, so thank you, Mr. Yu.
Okay, thank you.
Okay, thank you. And the last speaker is from the GTS AI Labs. Let's welcome Meng Jian.
Hello. Yep. So hello everybody. My name is Meng Jian. I'm a research scientist at Global Technology Service at Huawei. So first of all, welcome to Huawei, everybody. So today's presentation, we're going to cover a couple of things. So starting from with the topic of industrializing agentic RL, so domain-specific AI expert empowered by algorithm hardware co-design. Right. So given this topic, right? So we are running. Officially, So this is myself. My name is Jian. Again, I got my PhD from Cornell University this year, and before that, I actually spent some time in Meta and Texas Instruments a little bit. All right. So I'm joining Huawei as a research scientist, mainly focused on hardware, software co-design with good optimization algorithms and hardware, vice versa. Right, so overall, we're officially jumping to the era of LLM, right? Everybody knows that. And then, speaking of which, conventionally, when we start actually using LLM, we have one prompt and one output, right? So we can say, okay, this is one question, give me the answer. But now, since we jump into the era of 2025, we're seeing, okay, LLM model is not more like a chatbot anymore. We're seeing agents, we're seeing a lot of interesting applications using LLM as a guider rather than just like chatbot, right? So, given these kind of like agentic LLM versus non-agentic LLM usage, we'll start thinking about, okay, how are we gonna actually making reinforcement learning becomes more and more powerful in people's daily life? So that's what global technology services are doing right now. Okay, so let's jump back off a little bit and start actually thinking about what is reinforcement learning, right? So reinforcement learning, why and how. So starting from supervised fine-tuning, people know, okay, when I send in data, I can get outputs, and when I start predicting my next token, I can start let the model learn how to actually, how things works, right? But that actually just give the model know the distribution of the data rather than let the model know, okay, how to answer or how to solve problem correctly. So that's the key difference. Okay, so now if we look at the training of LLM model itself, we can consider it as a market decision process. Everybody knows that. And then when we spit in out tokens, we're considering it as a state and action. And rather on top of that, people start thinking about, okay, given the reward and given the environmental interaction, we can have the model learn how to reason, how to perform reasoning rather than just, okay, predict next token, right? So, longer or shorter, we're start seeing this kind of explosive manipulation and explosive method starting from, 2024 all the way to this year. So you can see Gork announced their, when the Gork 4 is announced, they noticed that, okay, reinforcement learning becomes like nearly half of the entire computing resource usage. Right, and now, it's expensive, and people having a lot of different kinds of methods. We have value model, we have a reward model, we have tons of models here. And how to make it simpler or actually model more, actually more hardware efficient. So many thanks to DeepSeek, we have GRPO. So GRPO kind of like it officially eliminates the value model, and then now we can compute advantage based on the group-wise advantage rather than just simple, rather than just expensive, reward model in itself. And the model learn from the group relative advantage instead of the per token value estimation. We actually enable a more hardware-friendly batch rollout and training. So by saying rollout, we're saying, okay, given the input, and we want to know the model behavior on top of that. So how to know that? So we can have the sampling process. By saying sampling process, we mean we can copy the input prompt multiple times, and we generate the output responses. And based on some temperature value setting, we will know, okay, the model characteristics look like this under this kind of circumstance. Okay, there's a lot of information here. Let's just break it down. Okay, so reinforcement learning. Okay, so we have the LLM model solely, beautifully sent right here, and then we know when we send in something, we get the output. And then when we start having the single term rollout conventionally, one-time response, right? Just like what I said, without agentic RL or without agentic LLM applications, we're just having one input and one output, and we have the group-based response during the training process. And on the other hand, when we have agentic or agents come into the picture, model needs to interact with all those tools, right? So the interaction, not necessarily to be like one or single shot. It can be multiple interactions and come back and get the reward. So we can have process reward, we'll have final reward. So there's a clear concept or clear separator in between. But on top of that, you can see when we start rolling out, the model is big, and input is also big. We have a lot of parallelism going on right here, and the data is big. The total number of data samples are enormous, right? And then how are we going to balance the hardware performance versus software efficiency? Software performance versus hardware efficiency, right? So different than the conventional or vanilla algorithm design at GTS, we're actually considering how to make it as a product. So by saying product, we're talking about how to balance the cost versus the overall price at the end. And apparently, computing power is a cost. It's part of the cost, at least. So here comes the infrastructure. So by saying infrastructure, we're talking about how to train the model with reinforcement learning, but in a very, very efficient manner. So you can see this is a MindSpeedRL example at Huawei, and we're actually building these building blocks by separating the entire training process into a couple of phases. So starting from the data loader, you can see we actually load the prompt and load the batch, right? And then we start doing the data transfer from one side to the other side, and now we have the model. The model start rolling out stuff, just like what I said. This is a sampling process. We need to know the model behavior. And based on that, we have this bouncing back data transition in between, and essentially what brings to the AI infrastructure is that how are we going to deal with the efficiency in between? As you can see from the flowchart in between, at the bottom of the slide, the AI infrastructure of reinforcement learning is actually packing up both training and inference, because we need to know the hard model characteristics first, and then move on to the training. So it is not like self-supervised learning, or self-supervised learning, supervised learning, or whatever. So we're having inference and training at the same time, and we're using different kinds of infrastructure. So speaking of which, we're having, for example, inference-dominant workload, such that we're leveraging VLLM Ascent or SGLang Ascent. These are very, very typical inference workload or inference infrastructure. And on top of that, once we got the trajectories or once we know how the hardware performs, now, wait, what? Now, we can have the training phase, right? By saying training phase, it means the trajectories or the rollout samples are going to send to the model itself. Like the model is offloaded on the other side, and we're using another set of infrastructure like Megatron or Mindspeed LLM from Huawei, right? And these kind of like transition could be expensive. And finally, the data transition itself, not just because it's not computing the trajectories or generating the trajectories is expensive, but storing them is also very expensive, right? And then, given all three kinds of aspects, now we need to think about a $1 million question, like which one is the most expensive one, and how are we going to make it efficient, right? So that's what AI infrastructure is doing. So, in summary, before we move on to the actual problem phase, we're at GTS AI, we're considering three different kind of problems from three different aspects. So first of all, in the agentic RL age, workload complexity is very, very important. Like we're mixing the workload of batch-based parallel rollout decoding, which means the model needs to generate a lot of samples, while we're having training process going on. And secondly, we have the data communications between. So you need to move the data from the data loader all the way to your inference workload, and then meanwhile, after the inference is done, you move on to the training phase. So this is very complex also. And finally, given all these kind of like multi-system connections, right? Multi-system connections, we want to make, given all these aspects, I want to, because this is an algorithm context, I don't want to be too engineering. So we want to give you guys some, basic understanding on, okay, why this is so complex, right? So let's jump into the rollout first, because rollout takes the batch-based input samples, and then we roll it out with the LLM model, right? So you can see the LLM model is going on right here, having deployed right here, and then when we send in data, they could be, the model could answer differently, even with the same question, right? We know all the probabilistic sampling right here. So we have one trajectory out. We might have a second trajectory out, right? So these two outputs could be different length, could have different length, right? Different number of tokens. And while the first one getting generated, I know it's in parallel, right? When the first one getting generated, when it's finished earlier, then we have to wait the second one. And now imagine if you magnify such kind of example to the scale of 128 samples, 256 samples, or even much larger batch sizes. What will happen, right? On the system level, you'll see a lot of idling. So that idling is what we call bubble. So bubble means when computing resource start doing nothing but eating your money, right? So that's how bubble works. And then now, although GRPO algorithm has demonstrated remarkable efficiency by eliminating the value model, just like what I said, but the overall training throughput and the updating frequency still heavily impact the overall efficiency of the RL system. So that is very important to us because we don't want, but it comes with a problem also. So, it comes to the problem also because, if we take a further look at the system level, asynchronous rollout doesn't solve the problem entirely because you still need to wait before you pipeline the data to the training. So again, there could be a lot of algorithm room to investigate those kind of optimization problems here. And that's the first one, right? So the first one we are talking about, how we're going to deal with this engineering problem on the infrastructure level. But on the other side, right, if we jump back a little bit to the algorithm side, from the conventional, or vanilla GRPO or reinforcement learning in the era of LLM, we're seeing, okay, when we generate a group of rollout samples by copying the input, into multiple copies and to get the model sampled out, we're seeing some of the cases where model doesn't learn at all. So if we look at the loss function of GRPO, we can easily tell that when all the sampled outputs has zero reward, absolutely, then there's no advantage. By saying there is no advantage, which means when the model doesn't actually, is not trained based on that sample because you're taking out the loss function with respect to that sample entirely, right? By saying advantage means, we're actually talking about how good the sample, how good the trajectory versus the other in a GRPO kind of like scenario, right? So, this is very, very bad because, like what I said, data are very, very important, and we don't want to lose them, and we don't want to waste them. How are we going to deal with this kind of problem? So this could be a very open question because this depends on not just the loss function design. I know we have for example, Alibaba got the GSPO or all the other fine-grained or cross-grained algorithm to overcome such kind of problem, but essentially this is not the end because in the era of agentic AI, just like what I said, we're having multiple stages or multiple interactions throughout the entire training process. That is, you cannot just easily solve these kind of problems because sometimes model just cannot learn the sample or just cannot answer the question correctly no matter how big or how hard you're going to try. So, I mean, ideally, right? So we want to solve that. Well, we're having, according to GRPO laws itself, if we take a look deeper into that, in summary, under the context of agentic AI, sometimes the model failed to find the right tool at each step. So when we have this kind of consecutive failure, right, it'll have problem because let's say you want to go to a supermarket and you have like a one interaction with one, for example, police officer, and he gives you the wrong direction because probably he got a bad mood, right? And then you go to another crosswalk and you have another wrong kind of direction. So under that kind of circumstance, if you have an accumulated error, you will not have the good destination at the end. So this is very critical, or even because based on our experience, this is even more, catastrophic, right? Because sometimes the model just needs a little bit more hint to get the right direction, but it just can't. So, well, I'll leave this as like an open question, but this is definitely worth to discuss. And finally, we're not here to just show the problem. We're here to show some progress. Throughout the couple of months in the year of 2025, we're actually building up a toolkit or infrastructure called 8Cube. By saying 8Cube, we're talking about Ascending Agentic AI. We're building up this infrastructure based on Huawei Ascend NPU. And it is a scalable and efficient agentic AI infrastructure designed for NPU cluster. We're enabling 200 billion LLM model for post-training with agentic RL. And we're seeing some efficiency out of it by overcoming some of the communication bottleneck or computing bottleneck throughout the entire system. So let me jump into that a little bit. So if you look at the bottom left figure, so we're actually having a very hierarchical design here. So at the top level, we have the agent interaction phase, where your rollout worker, like the LLM model, can get communicated with all these different agents, domain expert, math is just like a toy right here. But we're like what I said, we're having service, so the actual agents can be very, very complex. And then the rollout worker actually having the interaction with all these guys, and then we have the trajectory and we have the reward. And those rewards are going to have, our algorithm process so that we can have the good trajectory sent into the trainer. And in the trainer, we train the model, and like what I said, this data movement starts rolling out again. Well, we're not, building this entirely from scratch. Apparently, we're having some, basic infrastructure. For example, VLM Ascent, SGLang, and right now we're using MindSpeed-RL, but we're trying to support VRL in the very near future. So in summary, so the design hierarchy of 8Cube infrastructure can be, elaborated in the three phases. So first of all, we have the decoupled train and inference and agent call. So this partially asks my first question. So what if you have a bubble? So when the rollout becomes idle, what are you going to do? So right now, the most popular answer would be you let your rollout worker keep rolling out, right? So you just nonstop. So imagine you train the model and your data source is actually from a model. So that's how these things work. So you keep rolling out the data samples, and then whatever you got, once you reach some certain batch size, you send into the model for training, and boom, and wait for it until the next cycle. So by doing so, this is not like a very hard or fancy technique to think about, but we're actually making it very, very scalable. So you can support up from 32 billion all the way up to 671 billion model. And on top of that, we know, okay, disaggregation is good strategy. We can keep decoupling, right? What else we can do? So we can also decouple the prefill and decode phase by saying that, just a little bit background context. Once you have a prompt, you want to know the initial understanding of the model, so you send into the prefill to build up your attention map and everything. And then we can separate the prefill stage together with your decode stage, and then support the graph mode. And with that, we're actually maximizing the internal or intrinsic speed up of the model itself. And finally, like what I said, sometimes we're facing some problems that you just cannot solve. And the model also do the same thing. And how are we going to deal with those? One way, or one compromised way, is that, okay, we can have some sort of so-called online memory and row loss scheduling. So this can be very, very versatile. You cannot just limit it yourself on, okay, I'm just going to keep the skip the hard problem and keep the easy one. No, that's not how things work right here. We can have some smart algorithm design behind that, and so that we can filter out some non-informative samples while keeping those informative ones. And speaking of which, so we have some algorithm design actually tell, okay, when model just cannot learn, or we have some statistics tells that, okay, this sample is just entirely a tragedy, so we don't want to have that right now. So we can just temporarily skip that, and while maximizing our efficiency, because imagine you have a couple of epochs of training, your data loaders have a specific length, right? And you want to have a very, very good efficiency, so you can skip some of the samples that temporarily not learning, but you can jump it back eventually. Yeah, so actually a lot of things are happening behind. We're having a dogfooding right now, not necessarily open source right now, but we're doing that very soon. So we essentially, this entire toolkit or entire infrastructure is trying to solve one problem. So we're trying to make everything dynamic. By saying dynamic, it means we want to allocate the resource dynamically. We want to model learn dynamically. We want the interaction goes on dynamically, and eventually we want everything to be fully scalable and efficient, so people can just grab and use it. That's very, very important to the entire, no matter software or hardware environment of Huawei Ascend NPU cluster. Right. Yeah. So, let's have a little bit conclusion or summary right here. So different from single-term reinforcement learning, agentic RL right now involves consecutive tool calls during sampling. That's where all the complexity comes from. And the exploration path of sampling could be extensive and intentionally prolonged by the model itself. So let me explain that a little bit further. So sometimes, like what I said, your model just don't want to go further. And by not going further, it'll spinning out some random things. And so imagine they can fool you, right? So we don't want that to happen, and we want some algorithm design out of it. That's what things going on right here. And finally, I want to have a couple of open questions for, like, again, the latency challenge, right? Apparently, the challenge of long tail trajectory brings the bubble, and now it becomes even worse in the agentic RL era, because again, you have multiple interactions with your agents, and now throughout the training process, it could be very, very time-consuming. And the algorithm challenge is that what if the model doesn't know which step is correct or incorrect? Some verifiable reward would be very precious, but it is not always accurate. Solution and observations from our work is that, so fully decoupled of agentic RL training is good, and it's like very, very important in this phase. Like isolated execution maximize the power of orchestration, because you can always have an online scheduler and that tells you, okay, you need to process this data first before that one. And the observations, apparently, some stepwise verifiable reward are crucial, or is crucial to success agentic RL training, because you're having interactions and you want to know which one is correct. So final conclusion is that, under the perspective of the algorithm design, the importance of collectively optimizing algorithm infrastructure deserves more attention. So even though this is an algorithm context, I want people to actually dive into some of the engineering efforts that people have already been done. LLM now is a product rather than a pure technology. I believe everybody in this room understands that. So you're using ChatGPT every single day, and you're paying dollars for that, right? And build better infrastructure plus algorithm leads to lower cost and better profit. Because lower cost comes to electricity bills, water bills, and everything. And technical discussions, I would say, okay, we all want to train the model in a faster pace, but speed always comes with price, right? So from the conventional compression algorithm, we know if you compress something, you have to swallow those entropy loss or information loss over there. Given the sampling process, basically the rollout, it dominates the latency of the training process. With the price of ultra efficiency, what if the model is compressed and generate drifted samples to full precision training? Because you want the sampling process and training process to be identical so that you can have the on-policy training at the same pace, right? And then from the agentic RL perspective, what if the model consistently failed to generate the good samples? Without scaling the model size, how to explore the valuable trajectories? Because those trajectories matters most to train your model, so the model can know which one is good. Yep, so that actually concludes my talk. I'm open to any further questions, because I can feel it's a little bit faster. Yeah, cool. All right, questions?
Thank you, Mr. Meng. And any question?
Thank you for your talk. It is very fast-paced and pretty packed. So my question is, you have mentioned that you are able to find out which kind of data may not be needed or may not be, let's say, useful. That reminds me of a research published, I believe, recently, where researchers have found that a very small number of contaminated data can sometimes permanently or semi-permanently, let's say, mislead the AI models. So would this, let's say, a cube be able to assist with mitigating such issues? Because it will be very beneficial for the users.
Cool. Yeah, that's actually a very good question. So I'm gonna, like what you just mentioned, it's a little bit faster or too fast. Anyway, so we wanna actually look into this in 2 different perspectives. So first of all, by saying which one is valuable, which one is non-valuable, our primary goal is the efficiency oriented. So we want to see throughout the entire training process which sample that model already learned good enough, and we can use that part, or we can maybe leverage that part and skip temporarily. That's the first thing. And secondly, regarding which samples that model actually get drifted, right? We want to actually, if I actually jump back a little bit, so there's a very yellow block at the bottom right corner of this bottom left graph. So it says it's called online memory. So we're analyzing the trajectories and we're trying to see what the model sampled. Because we're not training the model based on some massively available data set. Some of the data samples are internally used before. So this is very, very critical because the data quality plays the most important role in the training process. And we want to monitor those. And I believe this is very, very important for all the kind of business. So if you want to have your own data to train your model, you need to know how model performs under your database, right? So this is very important. So to answer your questions, we don't have a very extremely clear solution right now regarding that problem. But what we can do right now is that we can use the online memory system as a feedback loop. Because we're having some data generation system to actually generating data for post-training process. We can use those online memory to guide the model, to guide the data generation process itself. So yeah, that's my answer. Probably not a perfect one, but we're working on it also. Yep.
Any other question?
Hi, thank you for your presentation. And I have a question. I'm just curious, does it make any sense to have a way to evaluate or estimate the progress of execution of some specific trajectory prematurely, so we could stop wasting resources on execution if we know that it's gonna fail with a high probability?
Okay. Again, a very nice question. So I think maybe because of the presentation, people are taking too much attention on the training algorithm and infrastructure itself, right? But where the training infrastructure actually built on, right? So it's actually built based on data, and we're making data, and we have another system at GTS to actually evaluate how good the data is. So basically, like what I said, the reason we want to introduce this kind of online memory or online trajectory manager is that we want to see, given the input data, how good the model performs under the current stage of training. That actually help us as a feedback loop. I think both questions are pretty much talking about the same thing. We actually want to use that part of the data to judge, okay, if that data sample is not good enough, we might just eliminate it. So again, this is not like we're training model based on deep scalar, math 17K, or some publicly available data set where they already been cleaned, tested by massive users. But we're using our domain-specific data set, and we're trying to make it profitable. So data could be very rusty in some cases, right? So that's why this system is special, because we can use RL to guide our data production. Yeah. So yeah, probably not fully answer your question, but feel free to follow up. Yep.
Are there any other question?
Oh, okay.
Thanks for the talk. I'd like to ask a more general question, given that you probably looked a lot into that. How far we are from AGI, and how much we would need to push to reach it, and could we just solely focus on agents and reach it using the agents, or we'll need to get some tech advancements? So generally, what's the biggest bottleneck? Thank you.
Okay, so just hold up here with your mic just a little bit. Yeah, sorry. Yeah. Well, that's actually a very good question, but like what I said, I just got my PhD. I don't know if there's one that I could be asked, how far are we from AGI? But that's okay. Again, so agentic AI is just one kind of method that we're trying to leverage to actually explore how good the LLM is to leveraging all kinds of tools. So that's my answer, because nobody knows LLM from now to AGI, maybe 50 years, maybe 5 years. But from my point of view, we're seeing some limitations of large language models, even your scale up. Because like what I said, we're not solving math problems. Just like the trajectories manager, if we go up a little bit to that domain-specific expert, even though just a one cube or one rectangle right here, it actually involves a lot of experts, including communication system expert, including programming expert, a lot of experts. But you can see the reason agentic AI comes into the picture, because we know the single model cannot solve everything. So that's why we have domain-specific expert, and we use the small model as the orchestrator. So that's my answer right here. So we're apparently not far away from AGI. Yeah. So that's my answer. Yeah.
What's your what's your time confidence interval when we reach AGI? Your personal.
My confidence interval?
Yeah.
About AGI?
Yeah.
Yeah, that's a good question. So I would rather focus on how to debug rather than consider how far away from the AGI, because let's just focus more on dirty works rather than just think about, okay, how far we're close from AGI, okay? Yeah, so I think everybody in this room are working on that right now, and this is why we're having this context. All right, cool, that's my answer.
Thank you.
Hello, I have a quick question here. Oh, wait. Oh. Yeah.
Oh, yeah, I'm sorry.
Yeah, sorry. I should have stood up. So my question is, basically, I mean, you mentioned about this, a data cleanup and this thing. So do you think actually data cleanup versus just giving it like a completely unstructured data or anything that is that you can fit in, in natural format, like cleaned up version versus uncleaned up version, does it actually make a difference? And which one is actually better, based on your experiments?
Right. So you're talking about like the data quality, right? So again, great question. So we are considering the data quality. Again, I'm not like a purely data department, but I can answer partially from there. So let's consider the unclean data sample sometimes as a noise, right? So there's a lot of like different types of optimization algorithm that can speed up the model, but it also introduces noise. And think about the noise as a random process, especially during the assembly process. So I would say something like this. So you can have some negative samples, right? Like considering about contrastive learning, right? We've been talking about contrastive learning for like 5 years. Not exactly 5 years, but yeah. So we're having this negative positive sampling, and we want to know which one is good by highlighting those positive samples. So we can intentionally inject some, maybe tiny a little bit noises over there, but not too much. And we're focused, actually the noises should be mainly come from the sampling process, because we use those trajectories to train the model, but the unclean data will impact the quality of the trajectories itself. We're not training that in the rollout phase. So again, to answer your question, the data cleaning at the beginning is very, very important because it guarantees the model can give us a good output. But in the training phase, we can have some noises over there. And that's where the off policy and the on policy, all this orchestration comes into the picture. So you can lag a little bit and then train the model again with a different version, right? So yeah, so that's my answer for that. Yes.
Hi, I'm Lydia. It's not a question, but rather an AGI remark, because I get triggered easily by that question. Stop moving the goalposts. We've been seeing that for tens of years, for maybe 50 years with the Turing test. Oh, when we will pass the Turing test, we've passed it in the 80s, but now we know that's not good enough. You cannot fake the Turing test by behaving like a teenager. You need to be smart. And now, are we at AGI yet? Yes. We're doing great. Thank you so much. Sorry about that.
Thank you. Thank you for that comment.
I guess that's a very good ending for there. Yeah, thanks, Lydia.
Yep.
Yeah, we are doing great, and hopefully we will be doing great. Thank you for your presentation.
All right. Thanks, everybody.
Okay, next we invite all of you to have a group photo together. Please stay on seats, and I have seen so many empty seats in the front. So if you sit in the back row, please go to the empty seats in the front rows. Please come here, and we will take photo from the stage. Okay, the back row, come to the front. We have empty seats in the front. 后面的人可以坐到前面来。后面的人可以坐到前面来，前面还有很多空位。Don't be shy. Please go inside the front row.